Hello, in this video, we will introduce minimum spanning trees. A graph may have many spanning trees. Suppose that the edges are weighted. A minimum spanning tree is a spanning tree with the minimum total weights. For example, this is a spanning tree for this graph, and the total weights here is 42. And this is also a spanning tree, and the total weights is 38, and this one is 38 also. So the 38 is the minimum, and this are the minimum spanning trees. Minimum spanning trees are not unique. We now design an algorithm to find a minimum spanning tree. This is called the Prim's minimum spanning tree algorithm. It works as follows. For the input, the graph, G consisting of vertices and edges with non-negative weights. Output is minimum spanning tree. Let V denote the set of vertices in the graph. Let T be a set for the vertices in the spanning tree. Initially, add the starting vertex to T. So T has now only one vertex. We're going to keep adding vertex into T. So y size of T is less than n, we're going to find V in T and U in V minus T with the smallest weight on the edge. So here's T, and we're going to add more vertex into T. So how do you find the one? You find the one that is adjacent to one of the vertices already in T with the smallest weight. So let's see how we find this. U is the smallest one, so we're going to bring U here. So this is the edge, UV is the smallest, so we're going to bring the vertex U here. That's the algorithm. It's a very simple algorithm. It's a greedy algorithm, so we always find the best and bring it in. All right, so this example, start assuming from 0. So which one I'm going to bring in? So the smallest is 5. Now, the next one, so you have 6, 8, 7, 12, and 6 is smallest. We'll bring 6 here in. And now which one is the next? Is 7, 7, 12, 10, so 7. So we can pick any of the 7. All right, and now after this, 10, 5, 7, 12, so 5. I'm going to pick 5. And then 8, 7, 12. So we have to pick 7. And then after that, you can have 8. Either this edge or this edge. So, and that is all the edges in the minimum spanning tree. Let's revise the Prim's algorithm and to make it easy to implement. So what I'm going to do is to get more details now. This time, we're going to start this source vertex S and let T be a set that contains the vertices in the spanning tree. Initially, T is empty. So we're going to add this data structure costs associated with every vertex. So cost 0 S is 0. So that's the one I'm going to bring in to itself. So this is 0. Cost V is infinity for all the vertices in V. So we don't know what's the cost to bring them into the minimum spanning tree. Now, size of T is less than N. Find U not in T with the smallest cost. Well, this is the smallest cost right now. So this is 0. So the source is brought in. Add U to T. For each V not in T and UV is an edge, we're going to check the cost. If the cost of this V currently is greater than the weight of UV, we're going to update it, this cost V, and change the parent of V to U. And the way this works is you can look at the animation for this. So let's go to look at the animation in the book. So I'm going to show you the animation now. This is the animation. We're going to start from 0, and the cost for 0 at this index is 0. All the others are infinity. So the parent of 0 is -1, indicating it's the root. Next, we're going to pick the smallest cost and add it to T. T is now 0. And with this change, we're going to now adjust the cost for 1 is now 6, and this 5 is 5. So all the vertices adjacent to this 0, now their cost is examined and updated if necessary. All right, after this, I'm going to pick the smallest cost remaining. That is going to be this 5. So 5 is going to be put it in. After that, you can adjust the cost. So to 1 is still 6, and to 6 is going to be 7, and to 4 it's going to be 12. So that is the change. And after this, we're going to pick the smallest cost is 6 here. We're going to add the vertex 1 here. Now, after you adding 1, and look, this is the cost for 2 is going to be 10, and there's no change to 6, is still 7. So this is here. And now we're going to pick 7 here. 7 is this. We're going to pick this is 7. So look at this 6, the parent is 5. So this is coming here, this one right here. So this is the one. And now with this change, the 2, the cost of the 2 now was 10, now is changed to 5. So next, you're going to pick this 2 and adjust the cost for 3, and for 4 is now 7. So which one you're going to pick is 4. And then after this, so there's one here is 3. The parent of 3 is 2. So this is the line. This is how the refined premise algorithm works, by adding this data structure and cost, and to track the cost. You always pick the smallest cost remaining to add it into T. Well, let's look at the implementation for this from here. I'm going to see the implementation in this. So let's look at the implementation. weighted graph, extends unweighted graph, and then go all the way down to get minimum spanning tree. So this is the minimum spanning tree. So here is the minimum spanning tree. So what is minimum spanning tree? It is this, it is the defined as this. This is the minimum spanning tree. It is a subtype of search tree. We add the total weights here, and also here a method to get the total weight. So you have a root, parent, search order, and plus a total weight for this minimum spanning tree. All right, look at the implementation for this right here. Is get the minimum spanning tree. Invoking this method, you can get the minimum spanning tree from, by default, let's go from the vertex index 0. And this is starting now from a given starting index and get the cost. So this is all the cost, infinity. So this cost is infinity. We assign this infinity into the cost. And the cost of the starting vertex is 0, and the parent is now defined, and the parent of the starting vertex is -1, and the total weight is so far is 0. And this is the array list to track all this vertex added into T. So this is T. We're going to expand T. T dot size is less than get size. So we are looking for one more vertex to add it into this. So what do we do here is to do this. And here, now, we don't know what is U now. We're going to find it. So there's -1 now. And current minimum cost is this. It's the infinity now. We're going to update this. So here is this. We're going to find if this vertex here is not in T and the cost brackets I is less than current mean cost. So that's the one we're going to find, that the current mean cost and also what vertex is this U. So after this is finished, so we have it. Now, if we don't have it, that means our graph is not connected. So we're going to break. Else, we're going to add U to T, and then the total weight is adjusted, and we're going to adjust the cost for all the neighbors of U. This is the implementation. All right, so here's an example now. The minimum spanning tree for this graph of cities and the ages, the distance between the cities. And this is the test program. We have all the vertices and the ages with weights. And this is the weighted graph using the vertices and edges. And now we're going to get minimum spanning tree for this minimum spanning tree. And now this is the total weight displayed. Thank you for watching this video. See you on the next video.